Greetings, everyone. Welcome back to the exciting world of physics. Okay, here's lecture 24. We're going to continue our discussion of electricity. And hopefully we're going to talk about electricity and matter, things called insulators, conductors, semiconductors, and superconductors. And hopefully we'll cover electric charge, electric current, and electric potential difference. Okay, so let's talk about electricity in matter. Electric insulators. An insulator is something that does not like to have electricity flow through it. So what's an example of an electric insulator? Well, this pen is made of plastic. Plastic does not conduct electricity very well. Rubber does not conduct electricity very well. A piece of wood does not conduct electricity very well. So what do rubber, plastic, wood have in common? Well, most of you, I'm sure, if I ask you, what is plastic? Where does it come from? The answer is, you probably don't know. Many of you don't know, and you've never ever thought about it, even though our whole world is surrounded by plastic, and everything we use is plastic. I'm going to tell you where plastic comes from. Plastic comes from petroleum, from oil. So plastic comes from something that is organic, that lived many millions of years ago, and was preserved in an oxygen-deficient environment, so it was the energy was still preserved many millions of years later. So plastic, wood, rubber are all organic materials, organic. Okay, what does organic mean? Organic, I'm going to write organic here. Organic just means carbon-based, lots of carbon. We'll learn that later when we discuss organic chemistry. So insulators do not like electricity to flow through them, usually made organic materials, not good insulators, not good conductors. A conductor, on the other hand, is something that likes to have electricity flow. So what's an example of a conductor? Well, iron, copper, aluminum, right? So these are all examples of metals. Mercury, liquid mercury, okay? So metals, in general, are good conductors, okay? So let's talk, if we can, about solids. What kind of solids? Well, this pen, this eraser, this book, this big nose, any type of solid, anything you want to talk about. All right? So a solid for us, very simple, right, is going to be a periodic array of atoms. A good word is a motif. How's that? Motif is a repeated pattern. Now, we have not discussed what an atom is, right? In a previous lecture, I mentioned that all atoms are electrically neutral, meaning the number of plus equals the number of minus. Once again, we'll be discussing this more in detail, all right? But for now, let me just tell you what an atom is. Okay? And this is the so-called Bohr model. Okay, Bohr, not in Bohr, the scientist, and it's like an atom. Atoms are tiny solar systems. What do I mean by tiny solar systems? Well, there's going to be something at the center, right? For the solar system, that's the sun, and then we're going to have things orbiting, but instead of planets, these are going to be electrons. I'm just going to write E minus here, E minus, negative electrons. This thing at the center has a positive charge. It's going to have things called neutrons. So this is going to be the nucleus. Okay? So we imagine the atom as this tiny solar system. Don't tell anyone, but I'm going to tell you now. This model really isn't correct, but it's good. It's a good model, and it'll help us with our picture. Okay? Now, when I said atoms are electrically neutral, that means the number of protons in the nucleus must equal the number of electrons. Atoms are electrically neutral. If an atom has too many electrons, or too few electrons, or it has a net charge, anything with a net charge is called an ion, right? Ions. Okay? Ions are charged particles. Cations and anions. And in the body, what are ions called? All right, you should know. I'm not going to tell you. Good. So let's look at a periodic array of atoms. I'm going to draw my nucleus like this. This is my little nuclei. Okay? And it's 3-dimensional, so I'm just drawing a couple of atoms. And then we're going to imagine electrons. Okay? These are electron energy levels. Okay, so the electrons on those atoms supposed to be going around. Again, it's just a silly picture. If I want this to be a conductor, what a conductor means, what that means is electrons from this atom hop over to this atom, hop over to that atom, and go through the system. That's what a conductor is. An insulator is one where the electrons do not move from one atom to another. So how could this be? What's the difference? Well, again, I'm going to give you a simple picture. Okay? I'm going to draw something here. This thing here is called the conduction band. It's not a rock band, it's called the conduction band. Okay? And it's like a super highway for electrons. What does that mean? It means if I can get one of these electrons up to there, then the electron will go through the system. But you see, from here to here is a gap. And it's actually an energy gap. E sub G gap. So, what happens in an insulator? Insulators, E gap, very, what do you think? Big. In an insulator, electrons, it's really hard to get electrons to get up to that conduction band to conduct electricity. So imagine your sneaker and you want to get electricity to flow there. You put some energy in your sneaker. Does it conduct electricity? No, it takes so much energy that you have to put in that the rubber starts melting before it conducts electricity. So in an insulator, this gap is very, very big. Well, let's look at a conductor. What would you guess that E gap is? E gap for a conductor. Well, conductors like to conduct electricity, so it doesn't take much energy to get the electrons to there. So in a conductor, E gap is very small. So it's easy to get things to conduct. Okay? What do you think a semiconductor is? A semiconductor E gap, it's like the three bears, not too big and not too small. Somewhere in between. Now, some of you may have heard of Silicon Valley in California. I'm not talking about Hollywood. I'm talking about Silicon Valley where they make semiconductors. Semiconductors, what they do is they can make this gap, this energy gap, to be anything they want. So for example, many of you have what's called solar calculators, not solar erasers. A solar calculator. What does that mean? It means the energy of visible light comes in, hits an electron, the energy of the gap is exactly equal to the energy of the light. So when visible light hits the solar cell, the gap is exactly equal to the visible light energy, and the electrons jump up and conduct electricity. Very simple. Growing up, watching TV, right? What did you do? You had to change the station, right? You had to get up and change it, and usually the handle broke, and you had to get the pair of pliers and change the station. Your father smack you on the head and say, get up and change it. Today, what do? We sit back, maybe a glass of wine, and do this, so our thumbs get a good workout. How does that work? Well, that remote is putting out energy. And in every TV, is a little circle thing with a semiconductor. And the energy gap in that semiconductor is exactly equal to the infrared energy that's going from your remote to there to change the channel. So the gap in the semiconductor on your TV is exactly equal to the energy being sent from that remote. Okay? Great. So, superconductor. A superconductor, I'll talk more about this later. When you put electricity, again, I'll talk about this more. When you put electricity through a system, when electrons travel through a system, it's like you going through the subway. When you try to get somewhere, what are you doing? You're going through and you're bumping against people. Now, every time you bump against somebody, it's like when you rub your hands together. What happens when you rub your hands together? Well, dirt comes off. Oh, besides that, what happens when you rub your hands together? Heat is produced. What is heat? Heat is energy. So if a particle goes through with energy and it rubs against things, it loses some energy. When an electron goes through a system, it's going to bump, essentially. It's going to lose energy. It's going to meet what we call resistance. Resistance means it's going to give off heat. Remember the second law of thermodynamics. So it's going to give off heat. And if it gives off heat, eventually, if you have a current going and you don't keep putting energy in, eventually the particle will die out. If you're going through a crowd and you keep losing energy and you don't eat and keep getting more energy, eventually you're going to collapse. So a superconductor is something, if you put electric current in, it travels magically, it goes through the whole system with no resistance. So a superconductor has zero resistance, therefore gives off zero heat, and therefore the electric current could last forever. I'll have more to say about that another time. All right. Let's go on and talk a bit about electric current. First, let me tell you what current is. Here's my simple definition of current. Current is the amount of stuff flowing, not very scientific, but that's okay. The amount of stuff flowing divided by the time it takes to flow. So it's the amount of something divided by a time. So let's give an example. Suppose I have a hose and I fill up a bucket. In 1 minute, I can fill up 5 buckets. So my current of water is the amount, 5 buckets. The time is 1 minute. My current would be 5 buckets per minute. Another example, train station on the L train in New York City. Lorimer Street, 3 o'clock in the morning, going through a turnstile. How many people go through the turnstile between 3 o'clock in the morning and 4 o'clock in the morning? Well, 6 people. So the current of people is 6 people per hour. At rush hour, say between 8 and 9 a.m., maybe it's 2,719 people go past the turnstile in 1 hour. So my current of people would be 2,719 people per hour. The amount divided by the time. That's our general definition of current. So what do you think electric current is? Well, logic would dictate that electric current is not the amount of stuff, but the amount of electric charge flowing in the time it takes to flow. Same definition, except for instead of stuff, I replaced it with electric charge. The symbol for electric charge is capital I. Capital I is what we use for electric current. The amount of electric charge, you remember our symbol for electric charge from Coulomb's law was capital Q. Q is electric charge. Time, T. If you recall, electric charge was measured in the unit called a Coulomb. So this is going to be coulombs, and our unit of time is going to be seconds. So the unit of electric current is coulombs per second, and this unit is called an ampere. So electric charge is how many coulombs flow per second, and that unit is an ampere, or people know it as amp. Okay? We're going to use this. We're going to come back to this. Okay? So hang on. So that's the definition of electric current. Now let's put two things together and then ask a question. We said that electric conductors, like metals, like to conduct electricity. So let's look. I don't know if you can see, but the top of this board and the bottom is made of metal, probably aluminum. When I touch this, I don't get electric shock. How come I don't get electric shock? We just said it's a metal and electricity likes to flow and it doesn't flow. Why? Well, let's look. Let's go back to gravity for 1 second. Here's my table, and here I have a mass, m. You and I agree, I think, that the potential energy here is mgh. That's its gravitational potential. If I put it on the edge, just put it there, we know it will fall. I also know that if I leave the mass by itself, this mass will never, by itself, jump up to the table. Never. Never. And we also know that this mass, if I leave it by itself, will never crawl over here, go to the same energy level, the same potential energy. So something will never go to the same energy level, and it will never travel to a higher energy level. It will only go to a lower energy level. And if you recall in an earlier lecture, I said, when we ask the question in science, why does a system do something? The answer is almost always because everything wants to be in its lowest energy state. Okay? So let's go back to this piece of metal. Okay? Let's look. All the electrons in this piece of metal are all at the same energy level, like this mass on a table. Every place on that table is at the same energy level. The mass will never move from one place to another. The electrons in this piece of metal will never go from one end to another end. Why? Because they're all the same energy level, the same energy. So if I want something to move from a high energy level to a low, to one place to another, I need to have a difference of energy. Let me use an example. Let's take this vodka. I mean this water. Imagine, if you will, imagine I just balanced this. I put the top on because I don't want to make a mess. Imagine I just balanced this, and it's just at the lip and going nowhere. So all the water is at the same energy level. So there's no current of water. Suppose I want this water to flow. What would I do? Obviously, right? Obviously, what I do is I would tilt this. Why? Because now this side is at a high energy level. This is at a low energy level. And so the water will flow from a high energy level to a low energy level. Okay? And that's the basic idea behind electric potential difference. Okay? Now let me give you another example. Let me show you something. All right? I'm going to draw a box. And there's going to be two sides. I'm going to put a little thing here and a little thing here, like Frankenstein's neck. This, I'm going to say, is a high energy state. High energy state. And on this side, I'm going to put low energy state. And then I'm going to connect them with a wire, a metal wire. Okay, let's look at a metal wire. Well, I said it's a metal, right? So I'm going to draw the wire something like this. And inside, there's a bunch of electrons hanging out. They're hanging out, right? Not doing anything. but they're really dying to move around. Right? So the electrons are here. If I connect the wire, remember all these electrons are hanging out in there, okay? All right, some are delinquents. I don't know what they're smoking, but they're hanging out. Nothing. Now, what happens when I connect the wire from a high energy state to a low energy state? Well, now, just like the water in the bottle, if everything's at the same energy, if I hold the piece of wire, there's no electrons don't flow. But if I connect one to a high energy state and the other to a low energy state, what do the electrons want to do? They want to go from the high energy state to the low energy state. So now, they start flowing, and I get electric current. Electric current flows. Yay! I. Now, electrons are not that bright. Okay, so what I'm going to do is, as they're going from a high energy state to a low energy state, I'm going to put something here and light it up. And what is this? This is a light bulb. So what happens is, if I put a light bulb in, the electrons go in, they hit the metal. Remember, they rub against each other. You usually have something with a high resistance, like tungsten. As they rub together, they start to heat up, and they glow. Why do you have light bulbs? What do you want to produce when you have a light bulb? The answer is, tricky question, the answer is light. But what else does a light bulb produce? The answer is heat. It turns out that a light bulb, old-fashioned light bulbs, produces about 90% heat and only 10% is energy. What do I mean by energy? Light. So we would say that this light bulb is 10% efficient or 90% inefficient. So if you spend $100 for lights, only $10 goes for lighting, $90 to the second law of thermodynamics, wasted as heat. All right. Last thing for this lecture is I want to tell you what electric potential difference is. I'll give you a definition. And I'll give you a symbol. So electric potential difference, we give it the symbol V, capital V. And it's the amount of work needed to move. Remember, if you move something, you're doing work. The amount of work needed to move a certain amount of charge. Oh, this is great language. Amount of electric charge divided by the amount of electric charge being moved. I'm not going to ask you to memorize this definition, but I want you to know it's work to move some amount of charge divided by how much charge you move. So I'm going to write this. V is amount of work. Remember, work was this. Divided by electric charge. So it's W divided by Q. Do you remember the units of work? Work are in joules. Q, electric charge, was in coulombs. So the unit to measure how much electric potential I have is joules per coulomb, which is called a volt. Okay? Volts. It should be obvious, I think, that the box that I drew before, this little box, with two sides with a high state and a low state, with two little things here, and a wire going across, and my light bulb, what is this box called? Well, it's called a battery. A battery. Now, what happens as this thing keeps giving off energy, losing energy, giving energy to the electrons? The high energy state keeps losing energy until it's at the same level as the low energy state. What happens then? The battery's dead, right? Things don't no longer flow from a high energy state to a low energy state. When they're both at the same energy level, the battery is dead. And when I say high energy state and low energy state, these are usually chemicals. And certain batteries have chemicals that can be re-energized, that you can put this back, right? Rechargeable batteries. Okay, but in general, when the high energy state reaches the low energy state, when at the same energy level, the battery is dead because electrons will no longer flow. Okay? This example, because the electricity flows from one side to the other, is called direct current, DC. So a battery is an example of a source of DC, or direct current. All right. So in this lecture, we talked a bit about the definition of potential difference, and we mentioned electric current. Right? Electric current is the amount of charge flowing in a given time. And V, you need a potential difference to get that charge to flow. If the entire system in your conductor is at the same energy level, no electricity will flow. You need to have a high energy state and a low energy state. I believe the textbook talks about potential difference, and electricity is like water, and the potential difference supplies the pressure to make the stuff flow. But I'd rather think in terms of energy differences. All right. In the next lecture, we'll get a little more mathematical and not as descriptive. So have a great one. Be safe and see you around. Peace.